All right, hello. I'm Sergey, the presenter of this paper for all of us. So Paymin is our joint student with Dr. Joy Paquette, and some of this work was actually based on the course I taught. So the other students graduate students who did this project jointly with Paymin as well. So we briefly mentioned this topic about this encoder that changes the JSON format into Forensic-Lucid in order for provide the digital evidence for investigation in a common format. So, and Gypsy is the system that's being used in that setup. So we'll quickly go through the brief overview and show the architecture, and the rest is in the paper and various theses as well. So this is the brief introduction for it, or maybe not so brief, so let's see. So we detail some of the things, how we encode JSON format, which is a JavaScript object notation, very popular in RESTful services today on social media platforms and other services, into another language called Forensic-Lucid. So we'll briefly describe that soon, what that language is. So we analyzed a number of requirements, both functional and non-functional, of what's needed in order to translate into Forensic-Lucid properly. We have a system, General Intentional Programming System, or Gypsy, that has compilers to parse and evaluate such expressions written in Forensic-Lucid. Then, since we plan to have this to be done at scale, and we already did we have this multi-tier architecture actually inside the Gypsy's runtime engine. So we extended that framework in order to support this scalability if we have to process a lot of JSON data. Now, why do we bother this? What's a real motivation for it? Is since I mentioned lots of RESTful so it's a representational state transfer web services are out there in different cloud service architectures, and JSON is a very popular format to transmit the data over these services. So in the case of incidents or investigations, one of the applications we're looking at is, for example, hate speech investigation. So if you collect comments on public posts, social media, or other sites that are fed through, for example, a RESTful API, like Twitter, we can collect volumes of evidence based on that and use it in an automated investigation manner. And there are other applications as well to that. So this is why, and Forensic-Lucid is the language that helps us to do with such as investigation. And that's why when we provide such an encoder that translates from one format into another, we need to also assure that the translation is faithful. So one application I mentioned already is a hate speech investigation. Another one, if you analyze fraudulent transactions on blockchains or others when the data are transmitted. So this is all can be used as evidence in a case. So briefly about Forensic-Lucid, we need to verify the encoders, let's say, because we represent the evidence, digital evidence for a potential digital crime. And if we do this transformation, and if it's questioned in court, we need to show that what we translated is actually correct and actual, and we did not introduce any new data during the translation process. So one option, and of course, is to teach the server software or applications to log their evidence directly in forensic Lucid format. In that case, we can avoid this translation of encoding from one format into another. But unfortunately, of course, many of them don't know about this format, and the logs have already been, let's say, produced, or the evidence have already been stored in the original format it was in. So we should still be able to translate. Now, what we're trying to do in this project with Paymin is to verify such translators to make sure that whatever the data they receive from a web service over the network is translated correctly into forensic Lucid. So there's a compiler for it, and it's a compiler framework called gIPC inside gypsy, and it has a induction engine, which is basically a runtime that can use different distributed middleware technologies to scale it. And our encoder that we can distribute through this middleware is also a member of that multi-tier framework inside the induction engine. The idea is to, of course, to be able to collect large volumes of data and convert them into forensic Lucid in a scalable manner, and then process it in a scalable manner. So, and that's where this general intentional programming system comes in, called gypsy. It started as a platform to evaluate different properties of Lucid family of intentional programming languages. The core property is the context. And in forensic Lucid, the evidence is the context. And we have operators to process it and evaluate it. It's implemented in Java, this system, and we use different Java middleware support for scalability. Different students try different middleware techniques to see which one does better for different things. It's also an open source system. So this is how the intended usage of this. So we have JSON data stream or a file that is the user supplies through the service, or the service collects starting from a root. Let's say our cases were a GitHub service and a Twitter, or other ones as well. There was a public repository as well. Then we generate forensic Lucid outputs, and we perform any kind of analysis, give it to the compiler, and then evaluate claims against this evidence. So this is the corresponding sequence diagram for it. It's fairly straightforward. There's nothing special to it. There are actually a lot more details to it, so that we are not presenting in this short presentation. And this is specific files and Java classes that are part of the engine, the induction engine inside gypsy. So a JSON converter DGT, it's a demand generator, and DWT is a worker. So when demand generator asks, okay, could you process these files, and then the worker goes, collects these files, and converts them into the forensic Lucid as a context file, and generates the generator gets final IPL file for further compilation. So these workers could be numerous, processing in a task farm pattern like manner all these demands. And so we had a few data sets that we worked with, and we're working to produce our own data set to showcase. But so for those who are curious how forensic Lucid looks like, it has some similarity with JavaScript object notation for its evidence declaration, but that's where it ends. The rest comes from Lucid. And JSON, we had a few static files, and we used these JSON datasets repository from Dorfson. We also looked into actual services of GitHub API if you want to analyze vulnerable or weak code or commits and have attribution, so that could be part of the evidence. Or Twitter API as well, let's say if you want to investigate hate speech and like that. And this is our big picture, how it all fits together. So the GFC part is on the right, so it has the engine, the GE, with the workers and generators, and a compiler part of it that basically produces an output called GR suitable for the engine to work with. So it's an intermediate representation. So gIPC then can compile forensic lucid models produced by different encoders, such as Json-Flucid encoder. And we have this distributed storage. So depending on the middleware used inside the engine, we supported different models using, let's say, Genie, Java Spaces. We looked into also Hadoop, it's with HDFS implementation. We looked into plain database and other ways of storing it. So different representations basically, which should be a scalable storage. So for the storage, we have something called DST. That's a data storage tier that is basically enables communication between the workers and the generators. And yes, so this design, architectural design, actually has been around for a while in Gypsy. And then on the left-hand side is something I'm not discussing in detail in this talk because it's user interaction with this system. It has to be scalable. Uses multimodal input and view and different representation, because forensic lucid in itself is like any lucid language, is a data flow language, so it can be represented as a graph and be programmed as a graph. So there is a way to interact with it to make it easier to write these programs as for the left side. So this is a big picture how it all fits together. And to quickly conclude, so we're doing now scalability testing and formal verification using tools like Isabelle Hall to verify this encoder specifically and generalize the way of working with it. And essentially we managed to provide this type of encoder for this JSON data. And there are sister projects as well that work with logs from switches, from Apache, from Nmap, from different network utilities as well. So they have the same situation. When you encode from one format to another, you have to show, no matter how you implement it, whether your encoding is correct if it gets questioned. So on this, I conclude my presentation. Thank you very much.